Welcome back for more. Let's talk about determinants of matrices. A determinant is a number that's kind of hard to describe its value right away. So first we'll just talk about how to find the determinant. The determinant is a single value that's kind of representative of what a determinant does. That's the best way I can describe it right now. But to find the determinant, the process is pretty simple. If it's a 2 by 2 matrix like this one is, you take 1 times 4 and 2 times 3 and subtract them. So the determinant is -2. When you see these absolute value looking brackets, you'll notice how this has like an actual bracket, this has 2 straight lines. This means determinant. It doesn't mean absolute value when you're dealing with matrices. It means you're finding the determinant. So don't think of that as absolute value. It doesn't make everything positive. I'm going to do 15 minus 0. The determinant of matrix B here is 15. And I can do 60 minus -6, which is actually 66. You do what I call the downhills minus the uphills. And that'll actually make more sense as we do a 3 by 3. But a determinant is basically, suppose you have matrix A, B, C, D. Well, the determinant of this matrix is AD minus BC, and that just gives you some number, and that number is the determinant. A determinant is a single number that comes out of a matrix, and again, it kind of gives you information about what the matrix does to things, and I'll explain that more later. I call it the downhills minus the uphills, and here's a 3 by 3 system. Well, we can't just do this minus this, because that leaves out a bunch of numbers. So instead what we do is we take these 2 columns, we leave the first, no, I have that backwards, I'm sorry. We take, gosh, I'm falling apart here. Come on, go back forward. Let's just clear everything. We take these 2 columns, and we copy them down again over here. So I'm going to have 2, 5, 0, 1, 1, 1. That was a bad 0. Now I'm going to do multiply and add these, multiply and add these, multiply and add these. So 2 times 1 times -2 is -4. 1 times 4 times 0 is 0. -3 times 5 times 1 is -15. That was all the downhills. Now we'll do it again for all the uphills. So I'm going to go 0 times 1 times -3 is 0. 1 times 4 times 2 is 8. -2 times 5 times 1 is -10. When I put all those together, -4 minus 15 is -19. 8 minus 10 is -2. I'm doing the downhills minus the uphills, so -19 minus -2 is -17. That is the determinant of that matrix. I would say it's -17. And now this starts to get confused with multiplying, because you're always doing like this, and multiplying, adding, multiplying, subtracting type thing. And so multiplication and determinants can get easily confused. So please work to keep them separate. I'm just going to make up another example so I can run through another one with you. If you feel like you're okay with this, go ahead and move on. But say we have 3, 1, 0, 4, 5, 1, -1, 0, 2. Having zeros actually makes this a lot easier because the multiplying by 0 is nice. Well, to find the determinant of this matrix, I'm going to copy back down 3, 4, -1, 1, 5, 0. Then I do the downhills and the uphills. It's always downhill minus uphill. So if you want to pause and do this on your own at this point, you can. But there's 30, -1, and 0. There's my downhills. Now I'll do the uphills. There's -5, 0, 8. Nope, this first one wouldn't be -5, because -1 times 5 times 0 is not -5. -1 times 5 times 0 is actually just 0. And so I ended up with 29 minus 8, which is 21. So I'm going to try and just make this as clear as I can. You're going to multiply all these numbers and then multiply all these numbers. Gosh, I said as clear as I can. This is like illegible. Multiply all the numbers on the downhills, and then add them up. Multiply the numbers on each string of uphills. So like I multiplied these, multiplied these, multiplied these, then I add those up. Then I took those two collections of things and I subtracted them. That is how you find the determinant. Now determinants have a few uses. One of them is to find the areas of triangles. So this triangle has 3 coordinates. It has a point -2, 3, it has the point 5, 5, and it has the point 7, 1. If I can make a square matrix out of this, so I throw a column of 1s over here to make a square matrix, and then I try to find its determinant, half of that determinant gives me the area, and I might have to switch the sign. So I should make it clear, determinants can only be found in square matrices. Determinants only work in square matrices. So what I did is I took the 3 coordinates, x, y, x, y, x, y, threw them into a matrix covering x and y's, and then I put in a column of 1s to make this square. And if I do 1/2 times that determinant, I get the area of this triangle. Now I had to do the plus or minus here because sometimes the determinant works out negative, so you just make it positive because you can't have negative area. And let's do this. I'm going to put a -2, 5, 7, 3, 5, 1 here. So then I'll do downhills minus uphills. So I'll do downhills first. This is -10 plus 21 plus 5 minus 35 plus -2 plus 15, which is then -10 plus 21 is 11, plus 5 is 16, 35 minus 2 is 33, plus 15 is 48, so 16 minus 48 is -32. So I'm going to take that -32 and do -1/2 times -32, and that gets me 16. The area of this triangle equals 16. 16 square units. So to find the area of a triangle, you can just take the determinant of the coordinates of the triangle and cut it in half, and then either make that positive or negative. And I've got extra credit posted online if you're in one of my classes about why that is and how that works that you can play with if you want. There's extra credit for other parts of this chapter as well. Finally, you can use the determinant as a dilation scalar. So here I've got a rectangle, and it's actually a square with these 4 coordinates. And I took those 4 coordinates and I put them in a matrix. So here's the point 0, 0, 0, 0. And here's 0, 4. And here's, well, think of it this way, 0, 4. It's going x, y. And then x, y for 4, 4, and 4, 0. I'm going to take those 4 coordinates in a matrix and multiply it by the matrix 2, 0, 0, 2. This matrix here. You'll notice the determinant of this matrix is 4. You do 4 minus 0, which equals 4. Well, let me do the multiplication and look at the new matrix. Row, column is just going to be 0. Row, column, 0. Row, column, 8. Row, column, 8. Row, column, 0. Row, column, 8. Row, column, 8. Row, column, 0. So I have new points now. I have the point 0, 0, 0, 8, 8, 8, and 8, 0. I just created a new box, a new rectangle, excuse me, square. Use the word square, Grant. This square here. If you notice, this square has an area of 8 by 8, which is 64. This square has an area of 64. This square had an area of 16. How much bigger did it get? It got 4 times bigger because the determinant of that matrix was 4. It's the scalar. The area changed by the determinant of the matrix. So when I say that a determinant can give you kind of indication of how a matrix can affect something, in this case, if you apply it to any shape, the determinant will change the area by that scale. I can show it another way. I want to find a picture that I can find and just, yeah, I'll show it to you again. Here's a picture. I realize if you've been watching these videos, you might not know what I look like. And so I wanted to grab a nice flattering selfie of myself. Here's me. That's a picture I took actually about 5 years ago. You can see it's like the original selfie because I had to use an actual like camera and then grab a cord and plug it in my computer. Anyways, the point is, ladies, I'm taken. Here is the picture, and here is a matrix. It's the matrix 1, 0, 0, 1. That's called the identity matrix. And you'll notice that the determinant of that matrix is 1. And if I take this matrix, and I'm going to type down here, I'm going to apply matrix T to this shape, and I'm going to call this pick 1, because that's what it's called. Nothing happens. It doesn't change at all. But if I take this matrix and I start to change it, I can take the first value 1 and now change it to a 2. Well, now the determinant, this here shows the determinant of the matrix. The determinant is 2, and the picture got twice as big. If I do this, now the determinant is 4. And as I move this around, you can kind of see one is 4 times bigger than the other. There's other things you can do also. If I make one of these negative, one of them gets flipped. And you can't even see it right now. I'll try and pull it up. But it got reflected over the x and y axis. So just a quick, silly demonstration of how determinants can show value, something that we'll play with in our homework. Thanks for watching again. Hey, you did it. You watched a whole math video, or you at least skipped to the end here. Either way, thanks for watching. I hope it was helpful. If it was helpful, maybe share it with a friend in your class who could also use it. You can subscribe to follow more videos. You'll see links popping up on the corners to watch previous and past and good videos. You can always leave a question down below or just add a comment. And I hope you have a wonderful day. Thanks for watching.